Welcome to lab here. As I mentioned when we finished lecture, I think we're going to continue lecturing on where we were at. Um, and I think what we're going to do is probably move the experiment scheduled for today to Monday. We'll talk more about it probably at the end here when we're done maybe lecturing for a bit. And that'll give us enough time to get to some of that topics that you'll need for that experiment. Okay, so like I said, we're just going to kind of continue on, and we'll talk about all the lab stuff at the end. But again, that's probably the game plan. Uh, Experiment 3, which I think was scheduled for today, I think we will probably move to Monday, and we'll take care of it on Monday, I think. All right, so we've been obviously talking about sort of the atom, electrons. We talked about today sort of moving away from Bohr's model of this sort of planetary model where electrons are in these sort of fixed orbits moving around in sort of circular patterns about the atom to this more quantum mechanical approach to the atom, which again, it basically takes advantage of sort of the idea of that dual nature of light where particles and waves basically have similar like properties, and particles like electrons can behave like waves. So we moved away from the idea of sort of for sure knowing exactly where electrons are in the atom, exactly to how they are traveling about the atom, to the idea of sort of Heisenberg and Schrodinger and all those guys, to this more probability of we don't really know exactly where an electron is per se in an atom at any given point in time. And we don't know exactly how it's traveling. And based on Heisenberg's uncertainty principle, the more we know about sort of one aspect of that, either how it's traveling or where it's located, the less we have sort of an information about the other aspect of it. And that in combination with sort of our wave functions brings up our idea of this more probability of, we can have a pretty good probability of finding these electrons in really these sort of theoretical sort of properties like atomic orbitals, S's, P's, D's, F's. And these again are sort of, probability maps, theoretical sort of places within an atom as to where electrons sort of will be housed. We talked about quantum numbers. The quantum numbers really are sort of the foundation for why we say there's only one s orbital, there's only 3 p orbitals, and why we say on the first energy level there's only s orbitals, on the second one there's p orbitals, that's where they start, third energy level d orbitals, fourth energy level f orbitals. So it sort of is the backstory, if you will, to electron configuration and sort of where sort of all those, 1s2, 2s2, and all those kind of things sort of come from, and sort of the order. We finished up sort of talking about the idea that, when we do get into sort of a polyelectronic atom, or it's a fancy way of saying an atom with a lot of electrons or more than one electron, because we do have that sort of negatively charged, near negatively charged sort of aspect occurring, it does actually have an effect on the energy levels of the individual sort of subshells, if you will, or orbitals within an atom. And we do get this sort of separation in terms of energy levels of, not necessarily energy levels, but just sort of energy locations of where they are sort of placed on the energy sort of diagram, if you will. And some orbitals end up being lower in energy than others. And that has an effect, again, on how the electrons are basically added to the atom. They are added from the lowest energy to the highest and kind of work their way up. The major sort of difference, as we talked about there at the very end, was where we get our S's to our D's. And the S orbitals actually end up being lower in energy to start out with, and they actually do get the electrons first, followed by the d orbitals, and we see that sort of pattern repeat. 5s before 4d, even 6s before 5d, and so forth. So we get that sort of repeating of that pattern that occurs with our sort of orbitals and how they are sort of filled. Again, I drew this here on the screen at the end of lecture, and the nice thing about this is it's something you can recreate pretty easily for yourself on a piece of paper. Again, if you just kind of go on the diagonal there, you know, S to start at 1, P start at 2, D start at 3, and F start at 4, and just kind of fill in below it, you can pretty much recreate the correct orders and stuff like that. We always start, as we were talking about there at the end, at the top, and we keep filling. If we need to fill more, we zigzag back and kind of go back and forth, kind of through this guy, filling it in. So if you know sort of that on the left, or are able to sort of recreate that for yourself, and if you know pretty much what we talked about earlier about how many electrons each orbital or subshell could hold, you should be able to write any type of electron configuration that you need. Remember that our max electrons for our s orbital is 2, p is 6, and that's really our subshell, right? D subshell, you could fill up with 10 electrons, again 2 in each of the d orbitals, and for f 14 electrons, again each in 2 in each of the 7 f orbitals that are present. So this would allow you to write really your electron configuration for really anybody that you would need to kind of do. So let's do that now. We're going to actually kind of talk about electron configuration and orbital diagram, and we're going to tie into it what we've been talking about, sort of the quantum numbers, so you can see again how they relate to each of the electrons that sort of go into the atom. So I'm just going to we're going to kind of do it here on this paper. It kind of will cover some of the other slides, I think, down the road, but we'll just kind of go through it. So why don't we start with hydrogen, which is 1. Hydrogen has an atomic number of 1, and in a neutral hydrogen, that also means that it has 1 electron. So we would definitely start at the very top there to write our electron configuration, and we would come down to basically 1s1 would be the electron configuration for hydrogen. As we've talked about before, the first number there is our principal quantum number. That's our N number. Obviously, the S is the orbital that the electron is in, and that is the number of electrons in an orbital or subshell in that particular case. We can also draw what is sometimes referred to as the orbital diagram. And the orbital diagram is a set of lines, or sometimes people use boxes and arrows to really represent sort of the electron configuration. So I'm just going to use lines. Again, some people use boxes. And we would have one line to represent our 1s orbital. And as we talked about before, the very first electron that goes in there will basically get that sort of upwards notation and would look like that. So that would be our orbital diagram there for our hydrogen. Any questions on that? Now we can, for this electron hanging out right there, we can write the 4 quantum numbers for it. And the 4 quantum numbers for this guy would be N would equal 1, again, because it's basically on the first energy level. L would equal 0 because it is definitely in a s orbital. Because L equals 0, as we talked about before, the M sub L for that electron would also have to equal 0. And now we see again that the electron is heading in the upwards direction, which means the spin quantum number for that guy would be +0.5. Again, not plus or minus 0.5 in this case, because we're specifically talking about this electron here. It is in that upwards orientation and would have a +1.5 for the spin quantum number. Any questions on any of that there? All right, continuing on, let's take a look at number 2 there on the periodic table. Number 2 on the periodic table is helium, which we sort of did earlier, but we'll add it to our list here. Helium is 2 for its atomic number, which also means, again, it has 2 electrons. Again, we always come back and start at the same spot. So we're always going to start here. We would come down and go. Now the configuration would be 1s2. Again, the first one is the principal quantum number. The s is obviously the orbital is in, and the 2 is how many electrons are in that particular orbital. If we were to do our orbital diagram for it, we would again have a 1s box. We would have a line that goes up there. And our second one, again, would need to go in the downward direction. The reason for that is, again, this first guy here has the same quantum numbers as we just did there. N is equal to 1, L is equal to 0, M sub L is equal to 0, and M sub S is equal to plus a half. Again, this guy's quantum numbers would be N is equal to 1, L is equal to 0, M sub L is equal to 0, and M sub S is equal to minus 1/2. Again, that difference in the spin is what allows both of these electrons basically not to violate Pauli's exclusion rule, and they actually do have 4 different quantum numbers and not the same quantum numbers. Again, a reminder, as we saw earlier, that if we decided that we wanted to place those electrons either both going upwards or both going downward, these both would violate Pauli's exclusion rule, as this electron here would have those 4 quantum numbers and this electron here would have the same 4 quantum numbers, and that would be a violation. And if we did the other guys, that electron there and that electron there would also have these 4 quantum numbers, which would be the same and also a violation. So again, that's sort of how we get around Pauli's exclusion rule. We need to put our electrons in the same orbital, heading in opposite directions in terms of their spin. And when we do that, opposite spins within an orbital, this again is what is referred to as being paired spin. Any questions on that there? Okay. So that is hydrogen and helium. Might as well continue on here. So let's take a look at what comes next, which is, I think, number 3. I think I can count there. That's lithium. So we'll go with lithium, which is number 3 on the periodic table. Again, that means that it has an atomic number of 3, which has 3 protons. Also means that to balance it out in a neutral atom, it should also have 3 electrons. Again, starting up at our top, and we can also see from our picture here, at this point, this orbital is definitely filled, which means we would need to zigzag back around and come to their next orbital. So if we do that, again, starting at the top, we would have 1s2, 2s1 in this particular case. Again, if we did our orbital diagram, we would need 2 boxes or 2 lines. I'm not drawing it correct in terms of energy just to save space, but technically, if you drew it correct in terms of energy, you would draw them, one on top of the other and that type of stuff. We would fill our first guy in here, our second electron in there, and now our third electron would go into our 2s orbital, heading in the upwards direction. Now, if we did our quantum numbers for this electron, the first 2 electrons would be the same quantum numbers as we just did. This third electron here would now have an N value that is actually 2. And that is because it is the electron specifically in the second s orbital, or in the second energy level. Remember that if N equals 2, L can equal 0 or 1 in this particular case. In this particular case, the L value is 0 because the L value of 0 represents an s orbital. The L value of 1 represents a p orbital. And this electron that we're talking about is definitely in a s orbital. So it would be incorrect to say that the L value for that electron would be 1, or possibly could be 1, because it is definitely not sitting in a p orbital in this particular case. Question on that. Because the L value is 0, that means the M sub L for that electron is 0. And we see that the orientation of that electron is heading upwards, which means the M sub S would be plus 1/2 in this particular case. Any question on that? Rolling through here to number 4, which would be beryllium. Again, starting at the top, 1s2, 2s2, as we can see there. If we do our orbital diagram, again, we would need 2 boxes or lines. First one going up, second one going down, first one going up, and now again, not to violate Pauli's exclusion rule, second one going in the downward direction there. The first 3 electrons are the same quantum numbers that we've previously done, so we'll just focus in on the last electron that's been added. When we look at the last electron that's been added, in this case, the N value here going to be 2 again, because it is still on the 2s orbital. L value still needs to be 0 because it is still in the s orbital at this point. The M sub L does need to be 0. And now the M sub S in this case would be minus 1/2. Again here, that making sure we do not violate Pauli's exclusion rule. And now our spins are paired at this particular point. Any questions on that? Okay, so continuing on here, we will go to boron, which is number 5. Again, as we can see from above, we are filled, which means in this case, we will then have to zigzag to our 2p next. So doing that gets us 1s2, 2s2, 2p1 in this case. Again, if we're doing our orbital diagram, we would need a 1s, we would need a 2s, and remember that our p subshell has 3 orbitals, so we would need 3 sort of lines or boxes. One represents the px, py, and pz orbital. First electron would go in, up, and then down, up, then down, and our first electron would go on the left here into that particular orbital. So now let's talk about what are the numbers for this particular guy here. Well, we do know that it is sitting in a 2p orbital. That means that n does need to equal 2. We know that when n equals 2, we could have a value of 0 or 1 for L. In this particular case of that electron, it is sitting in the p orbital, which means that the acceptable value for L is actually 1 in this case because it's sitting in the p orbital. Now, when L equals 1, M sub L can equal -1, 0, and +1. So how does that sort of work? Well, when we look at the orbitals here, they pretty much go in that order. This is -1, this is 0, and this is +1 in terms of the M sub L number, which now we can see that our electron is sitting in the -1 for the M sub L. And that means that our spin would be +1/2. Any questions on how we got any of those numbers, electron configuration, orbital diagram there? Okay. Then continuing on, we did boron, so we will go to carbon there. That's number 6. And carbon being 6, again, having 6 protons would have 6 electrons as well. That gives us a 1s2, 2s2, 2p2. So when we look at this, we have a couple of electrons on the first energy level. On the second energy level, we actually have 4 electrons happening. You could count the top numbers to know how many electrons you're dealing with. If we were to write our orbital diagram, again, a 1s box, a 2s box, and a 2p box, 3 of them. And our first one would go here. Second one would go here. First one will go here. Second one would go here. And at this point, we have to put our first one here. We do have some options as to where we could potentially place our second p electron. You may be tempted to go, well, it would make sense to place it here and pair it up. Or another option would be we may not pair it up and we actually may be going in one at a time. And there is actually another rule that kind of helps us decide which way it's going to kind of go. And that is what is referred to as Hund's rule. So Hund's rule is the rule that says the most stable sort of arrangement for electrons within an atom is one where we maximize parallel spin. So if you remember, when we pair off, that is what is referred to as paired spin. Where we don't pair them off, this is what is referred to as parallel spin. So what that tells us is when we have a subshell where we have multiple orbitals, the most sort of stable arrangement for how those electrons will go into those orbitals is they actually will fill each individual orbital 1 electron at a time. And once each individual orbital is filled with electrons, they then will come back and pair off. So essentially how electrons will go into a subshell like a p orbital, like a d orbital, like an f orbital, is they will go 1 at a time in the upwards direction until they're all filled. And then they'll come back around and start pairing off at that particular point. So what that tells us is we would not want to do that. Again, that would violate Hund's rule. So when we get to something like carbon, that 6 electron will actually go into the orbital next to it, also in the upwards direction. Any questions on that there? So again, we'll just focus in on the last electron added. And if we want our quantum numbers here for that particular electron, n would equal 2, again, because it's on the second energy level. L would equal 1 because it's in a p orbital. And now a reminder that this is -1, 0, and +1. That means that we could see that our electron here is in our m sub L of 0, and it's also going in the upwards direction, which means m sub S would be +1/2 in this particular case. Any questions on that there? So you can start to see probably that you get very, very specific with sort of quantum numbers and relate them to each individual electron. And again, by following sort of Pauli's exclusion rule and all those kind of things, every single electron essentially will have 4 different quantum numbers, although they may share very similar sets of quantum numbers or some similar numbers in there because they're in the same orbital. There will be that sort of difference that will occur really based on the spin and where they're at. All right, might as well finish up the first 10 there. So let's go with nitrogen next and see what we got going on there. So nitrogen is number 7. So our nitrogen here is number 7. Again, meaning that it basically has 7 electrons to balance out those protons. Starting at the top, 1s2, 2s2, 2p, a lot of math there. I'm going to go with 3. Sounds like a winner. We could count the top. 2 is 4, and 3 is 7. Giving us, again, our orbital diagram that looks something like this. Again, not drawn perfectly in terms of energy, but up and down is paired. Up and down is paired. Again, here we would be maximizing our parallel spin by putting one electron into each of those p orbitals. That is a grand total now of 7. Looking at our last electron added as to its quantum number, again, our n is going to equal 2. Our L will equal 1. Again, -1, 0, +1 in terms of our m sub L. And we see that our m sub L is +1. And we see our m sub S is +1/2. Any questions on that one there? Okay, so why don't you take a few minutes and why don't you finish up the first 10? Why don't you do oxygen, which is 8, fluorine, which is 9, and neon, which is 10. Why don't you do the electron configuration? Why don't you do the orbital diagram for that? And why don't you do the quantum numbers for the last electron added? So take a few minutes and then we'll go over it together and make sure everybody's on the same page there. Which is kind of where we left off. Let's see here. All right, so oxygen does have 8, which means it should do an electron configuration 1s2, 2s2, and 2p4 in this case. And by the way, that is how you should write electron configuration. You shouldn't capitalize everything. Should be using superscripts. There shouldn't be like dashes or commas or people like to do all kinds of weird things when they write it. So it should look like that in that sort of order. So if we look at our orbital diagram for this, again, we'll just draw it straight across for saving some space on the paper. Again, in reality, upwards it should go. But we would go 1 up, 1 down, that is full. 1 up, 1 down, that is full. And what we got there? 4 there. So 1, 2, 3. Now, once we put 1 all the way up to sort of satisfy Hund's rule, we then will go back and put our last electron back in the first box there on the left-hand side. That then means that if we look at the quantum numbers for this last electron that was put in there, this is going to have an n value that is 2, again, because of the 2 that's there. It is in a p orbital, which means that the L value here will be 1. Again, remember that because our n is equal to 2, as we saw before, L could be 0 or 1, 0 being an s orbital, 1 being a p orbital, and because this electron's in the p orbital, it has to be the 1 value. Now the m sub L basically goes like this, and we see now that our electron is back over there on the left-hand side, which means the m sub L would be -1, and the spin is now down, which means the m sub S would be -1/2. And that gives this electron that we just put in there, I think we got it if we go back, where is he? Right there. Different quantum numbers than the first electron that went in that box, which would have these quantum numbers. The difference being, again, the spin quantum number is the difference here. Any questions on that there? So let's take a look at fluorine, which is 9. So fluorine there would then be 1s2, 2s2, 2p5, giving us our orbital diagram of something. There we go. 1, 2, and 3. Again, up and down is full. up and down is full. Now we're going to go one at a time in our upwards direction. We fill this one in. Next one would then end up over there in the center orbital that's going on. And in this particular case, we'll look at this number here, hopefully answer a couple of the questions that just came in. But again, our n here would equal 2. Our L again would be 1 because it's still sitting in the p orbital. Now our m sub L, which again is technically the orientation in three-dimensional space, also tells us, as we talked about, how many orbitals there are. But the m sub L for the p orbitals, this first one is -1, second one is 0, and the last one is +1. So again, because we're specifically talking about that electron in really that second orbital, which is, this is the px, run that room, this is the py orbital, and this is the pz orbital. Basically hanging out in that py orbital has that m sub L value of 0, which basically tells us that that electron is in the py orbital, the orbital sort of on the y-axis in three-dimensional sort of space. And because the electron is pointing down, remember that the spin quantum number, which I think was a question I saw there, spin quantum number is always a half, no matter what orbital you're on, what energy level you're on. And the plus or minus basically indicates sort of which way the electron is heading. Plus is always the first one that goes in, kind of designated as going upwards in terms of a spin, and negative is always the second one that goes in, basically indicating that it's going downward. And here this guy would also have a -1/2. So again, when you're talking specifically about an electron like we are here, you do have to choose plus or minus a half. You can't put both, again, because they do represent different things. Question on that particular one there. Okay. Then the last one that we're looking at to finish out the first 10 is neon here. I think I'll flop the page there and do it over here. So neon is 10. So again, going back to our sort of zigzag guy, we always start up off the top. We could also see just from kind of continuing on, we pretty much have room for one more electron, and that's going to be where it's going to end up. So we would have 1s2, 2s2, 2p6. Again, if you count up the top, that's 2, and 2 is 4, and 6 is 10, giving us our orbital diagram that looks something like this. Up and down, again, going upwards first, now coming back and pairing off, putting obviously our last electron right there in our p orbital, our p subshell, and we see now that it is basically filled up completely. So if we do this, we are going to look at the quantum numbers here for our last electron that went in there. N would equal 2. L again would equal 1, as it is still in the p orbital. Again, our m sub L, which are these numbers that I'm putting on the bottom, again representing our really px, py, and pz orbital, are the sort of three-dimensional orientation of it. We see that that electron is in the +1, and we see it is going down, which means it is -1/2 for our spin quantum number. Question on that one there. Okay, so that's the first 10 electron configuration, orbital diagrams, and quantum numbers for each individual electron as we go through it. Why don't you try one more here just to make sure. Why don't you do, let's do calcium. Calcium is number 20. So why don't you again do the electron configuration. Why why don't you also do orbital diagram? And while we're at it, why don't we do the, I don't know, let's do the 15th electron. What is the quantum number for that guy? All right, so take a moment and sort of come up with that, and we'll talk about it. Okay, so let's take a look here. Let's just start with the configuration. So again, we're going to start at the beginning. So that would take us back to obviously 1s2. Then we would go to 2s2. We would zigzag back to 2p6. That's sort of where we left off. That gave us basically 10 electrons if we count the top. The next, if you follow the zigzag guide there, will take you to 3s2. So now it puts 12 in there. And next would go 3p6, which now takes us to 18 if we take up there. And now 4s2 would be our electron configuration. Now, I know I sort of asked you to do the orbital diagram, and I'll do it here in just a second, but I'm actually going to go to this question first just to kind of show you what you could do, you know, if you weren't asked to draw the orbital diagram, but you need to figure out some things like what are the 4 quantum numbers for the 15th electron. So I'll kind of do it a little bit out of order here just to kind of show you kind of what you could do to help you maybe visually figure it out without having to draw everything in terms of the orbital diagram. But we know that the 15th electron, this is obviously 2 electrons. That is 4 electrons. That's 10 electrons. That's 12 electrons. And then that is 18 electrons. That means that my 15th electron is sitting right here, really in my 3p subshell. So I know I asked you to draw the orbital diagram for everything, but if you weren't asked that, you could actually just focus in on just the 3p subshell part of it. And we know that the 3p subshell has 6 electrons that are put in there. And those 6 electrons would go in such as this: 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, and 6 electrons, right? So if we were trying to figure out which one is the 15th electron, we know before we get to the p orbitals, we have now used 12 electrons, which means that if we were to sort of count as we were filling this guy up, 12 electrons, this would be 13, this would be 14, and now this guy right here would be the 15th electron that would be placed in there. So we could kind of just draw this part of it, and we know that we are now talking about this particular electron here, which would be number 15. And we want that guy for our 4 quantum numbers. So again, if you weren't asked to draw the orbital diagram, you could just try to figure out where is that electron in terms of what orbitals, and then you could kind of just draw that aspect of it. And again, because you know the proper way that those electrons should fill those orbitals, you could basically narrow in on which one would be, obviously in this case, the 15th, or whichever one you may be looking at. So since we did that, we're asked to draw the whole thing, we would obviously have a box for our 1s. We would have a box for our 2s. We would have 3 lines or boxes for our 2p, which would also fill in one at a time and come back. And then our 3s box would go in. And then obviously what we just did there with our 3p box, and then our 4s box, again, not drawn correctly in terms of energy. If it was, it should be going upwards and that type of thing. Any questions first off on the orbital diagram there? So now that we sort of isolated our electron that we want to write the 4 quantum numbers for, let us see what we end up with. Well, that electron is sitting in a 3p orbital. That means that we know for sure that n is equal to 3. Because n is equal to 3, remember that L can go from 0 to n minus 1. That is 3 minus 1, which is 2, which means we could have an L value that could be 0, 1, or 2 in this particular case. So remember that when we're talking about the L quantum number, which is the angular quantum number, a value of 0 is an s orbital, a value of 1 is a p orbital, and a value of 2 is a d orbital. Since clearly this electron is sitting in a p orbital, the acceptable value for that electron should be a value of 1 only, not all three numbers, but just 1. Because m sub L would be -1, 0, plus 1, we see that that electron is actually sitting in the pz orbital, which would be the m sub L of +1. And we also see that the spin is going upwards, which means the spin quantum number would be +1/2. Any questions on how we got any of those numbers there? Any questions on sort of electron configuration, orbital diagram, tying in the quantum numbers to those things? As you can see, again, you could get very specific about, what this quantum numbers are for an individual electron. Any questions on any of that there? Okay, so while we're talking about electron configuration, let's also talk about another sort of way the electron configuration. Yeah. So the question is, what is L? So L is so remember that N is basically the principal quantum number, which is like the energy level. Right? L is the angular quantum number, which is essentially it's really the type of orbital. So when we talk about L, N could have values of 1 through 7, basically. L could have values of 0 to n-1. So you could technically have values of L that are like 0, 1, 2, 3, 4, 5, and 6, basically. And if you have an L value of 0, what that really means is you're talking about basically an s orbital. If you have an L value of 1, you're basically talking about a p orbital. If you have an L value of 2, you're talking about an electron in a d orbital, 3, an electron in an f orbital, and so forth, alphabetical after that point. We probably won't get into that with normal electron configuration, but that's basically what you're talking about. So again, when we look at the last one that we just did, we're specifically talking about this electron here. And this electron here is in a 3p orbital. And because that electron is in a 3p orbital, that tells us that our n value is going to be 3. And as we just talked about, possible L values when you have a n value of 3 is you can have a value of 0, 1, and 2. What that basically is saying, when you go to the third energy level, where's that picture there? Right there. Oops. Actually, it's right there, I think. Come here. When you go to that third energy level, you have a choice really of an s orbital, p orbitals, and d orbitals. And that's really what 0, 1, and 2 sort of represent, is on that energy level, available to everybody are those orbitals. S orbitals, p orbitals, d orbitals. Those are what are available. Does that mean that everybody's going to use those orbitals? It doesn't mean that they're necessarily going to actually use those orbitals, but they are available to them. In this particular case, this guy used the p orbital. And because that electron is specifically in the p orbital, we would have to choose the L value of being of 1 to indicate that the electron's in the p orbital. And the rest of it is, when we talk about it being a p orbital, the m sub L is basically the different numbers of p orbitals there are, right? So in a p subshell, there's 3 different p orbitals. And what we're telling people is it's actually hanging out in the third p orbital, which is really the pz orbital, is where that electron's hanging out. And it was the first one in there, and it has a plus half spin. Other questions on that? So if your question is, in this example, if you were to choose L value of 0, for example, so if you're asking, hey, let's say the L value was 0, what that would mean is you are no longer talking about the electrons in this subshell. It would mean that you actually would be talking about the electrons in this subshell. This would be an L value of 0. This is an L value of 1. And if you had an L value of 0, it would mean you were out. You're still on the third energy level in this case, could be, but you would then be in the s orbital that's on the third energy level. And these would be the electrons that would be in there, which would be L equals 0 and either plus a half or minus a half. So that's what would happen if you were talking about L equals 0. You would actually not be in that subshell of P, but you would actually be in the 3s. Would 4s still have an L value of 0? It would be. So if you're sort of talking about, let's say now we, in this example, moved over to these electrons over here, a couple of things will actually change on this particular one. So let me just kind of get crowded here. I'm going to go back over here, and we'll just focus in on those guys, right? So let's say we then want to know something about these guys. What we see is these guys are actually in a 4s orbital. So a couple of things actually change here. The n value is actually the 4 because of that. And because the n value is 4, L could have values of 0, 1, 2, and 3 in this case. Again, this representing an s orbital, this representing a p orbital, this representing a d orbital, and this representing an f orbital. And that's because if you remember when we got to the n equals 4 level, what is available is a 4s orbital, 4 p orbitals, 4 d orbitals. I'm running out of room. Imagine there's 7 dashes there, 4 f orbital. So basically when we say, hey, we're on the 4th energy level, all of these orbitals are technically available. Does it mean that they're going to be used? No, that doesn't mean that all of them are going to be used, but they're all available. So in this particular case, when we're talking about these two electrons here, we're specifically talking about electrons that are in the s orbital on the 4th energy level. And that would be represented by an L value of 0, if that was sort of your question. And because the L value is 0 in this case, remember that the only possible m sub L value would be 0, and the m sub s would be plus 1/2 for this electron. And if we did the same thing for the other guy, also sitting in our s orbital, the m sub s would be minus 1/2 for that second electron that's here. Other questions on that?
Professor, I have a question. On the previous slide, so you know how you got the n equals 3, L equals 1, that portion, the one that you circled or boxed. So is that for the 15 electron, what quantum number?
That is. So if we're talking about, I got a lot of boxes. So if we're talking about this box here, yeah.
Yes.
That box is the 4 quantum numbers for the original question, which was, what are the quantum numbers for the 15th electron?
How come we didn't do it for the calcium of 20 like we've done previously?
Oh, I just happened to pick randomly on this one, 15. I could have picked anyone. I just picked a random number. You could do it for the 20th electron. The 20th electron would be this guy here. And so it was just the question I picked. I just randomly picked whatever electron we were going to do it for. So you can do it for every single electron, all 20 of them if you want. You could write the quantum numbers for all 20 of them if you like. But in this question, I just randomly picked the 15th one as to the one that we're doing. Other questions on that? Okay, so let's see here. Let's talk a little bit about electron configuration and another way sometimes it's represented. So let us look at, let's take a look at the one we were just looking at, which was calcium. And calcium was 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2 there. Now, if we do sort of focus in on sort of the first part of this configuration up to here, and we count up basically the electrons that are there, that is 2, 4, 6, 8. Who do we appreciate? We'll try that here again. 2, 4, 10, 12, 18. And 18 electrons, if you look on the periodic table, is argon, right? Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So a shorthand that we sometimes do is we would put something like argon in brackets, and that would indicate that we have the configuration for argon, and we would continue it on. Argon is a noble gas, and sometimes this is referred to as noble gas configuration, where we take the noble gas, which is group 8 on the periodic table, helium, neon, argon, krypton, those guys at the end, basically 2, 10, 18, 36, 54, and we put it in front and do sort of a shorthand in terms of it, and that's another way that the electron configuration can be written for calcium. For example, if we look at sodium, which is 11, that is 1s2, 2s2, 2p6, 3s1. Looking at that configuration up through here, that is 10 electrons, and 10 electrons is neon on the periodic table. That is a noble gas, and we could write 3s1. So this is a sort of shorthand, if you will, that is sometimes used, and we used our noble gases, which is group 8 on the periodic table. That is the very last group where we have helium, neon, argon, krypton, xenon, and so forth, group 8 on the periodic table. And you could kind of do that shorthand if you want. You know, if you had, say, lithium, which is 3, though most people probably wouldn't shorthand lithium, but 1s2, 2s1, that technically is helium, and you would do helium 2s1. So again, you could kind of do this shorthand, sometimes referred to as noble gas configuration. You basically go to the noble gas that comes right before the element you're writing the electron configuration for. You put it in brackets, and that represents the electron configuration for it. And then you kind of continue on with the configuration. Question on that there. Now, so far we've talked about stuff that is obviously neutral. So what happens if we end up with something that's an ion? So we talked about ions before here. Ions obviously being things that have charges. We talked about 2 types of ions, cations and anions, right? Cations, which are positively charged, lose electrons. So our cations lose electrons, become positively charged. Our anions gain electrons, become negatively charged. And if we do have an ion and we want to write the electron configuration for our ion, we do need to take into account the charge that you have on there and adjust the electron configuration accordingly. So for example, we had calcium. So let's take calcium, which forms a +2 charge. So calcium with no charge has 20 electrons. Plus 2 means that it lost electrons, and it lost 2 electrons, which means it would have only 18 electrons. And that would be a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. That is 18 electrons, which is argon's configuration. Now, if I had something, say, like phosphorus with a -3 charge. Phosphorus with no charge is number 15 on the periodic table. Minus means that it gained electrons. 3 means it gained 3 electrons, which means it would have 18 electrons. And it would have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Or again, that is argon's configuration. Now you may be saying to yourself, they both have the same electron configuration. And the answer to that is yes, they both do have the same electron configuration. Calcium with a +2 charge, phosphorus with a -3 charge, and argon. They all have the same electron configuration. And basically something with the same electron configuration is what is known as being isoelectronic with each other. Isoelectronic means multiple things that have the same electron configuration. And you may be wondering, well, they both end up in the same sort of electron configuration. They both end up in argon's configuration. Argon is a noble gas, and you might remember noble gases are chemically inert. If you remember, for bonding, for example, the magic number is 8, like group 8. Everybody pretty much, and this is pretty much the basis of all types of bonding, ionic bonding, covalent bonding, where we share electrons. The whole goal of everybody in terms of bonding is to essentially end up at the same electron configuration or a same electron configuration as a noble gas. So in the case of calcium, it would give up 2 electrons in an ionic compound. And what that would do is it would move backwards to the noble gas that comes right before it on the periodic table. So if you look at the periodic table, calcium is number 20. If you go backwards 2, it goes back to the noble gas, which is argon, that comes right before it. Phosphorus gains 3 electrons, goes forward in an ionic compound to end up with the same electron configuration as argon. So if you look at the periodic table, 15 is phosphorus, forward 3 is argon. And by losing and gaining electrons in an ionic compound, when you have a metal and a non-metal, the purpose of that is that allows everybody to basically achieve the same electron configuration as a noble gas. And that's essentially what happens with metals. Metals in ionic compounds lose electrons and go backwards to the same electron configuration as a noble gas that comes right before them. And non-metals gain electrons and go forward to the noble gas that comes right after them. Again, the goal there is to basically achieve the same electron configuration as our noble gases. When covalent bonding, as we'll talk about, they share electrons, and by sharing electrons, they're able to basically come up with the same electron configuration as a noble gas. Any questions on things with charges? So guys, with charges, you do have to obviously adjust the electron configuration by either adding to it or removing electrons. And if we're talking about the representative elements, not the transition metals, which are kind of in the middle, but everybody will pretty much end up there at a noble gas in terms of their configuration. Any questions on that there? So we're talking a little about the periodic table and a little bit more about some of the stuff that we've been talking about as well. So the periodic table obviously was constructed to put things that have very similar sort of properties together. They left spaces. Mendeleev basically created kind of our current version of the periodic table, left some spots open to kind of fill in as we went kind of through things. And again, like I said, we sort of cover some of these slides here with what we just did in terms of electron configuration, orbital diagrams and stuff like that. But the Aufbau principle is one thing that we didn't talk about, but it's sort of what we were doing. The Aufbau principle is the idea that kind of like how the nucleus is sort of a build-up sort of principle that, protons are added one by one to the nucleus. We think about electrons sort of doing the same thing. We add sort of them one by one, kind of lowest energy to the next lowest energy to the next lowest energy until they're kind of filled. Obviously, we've done our electron configuration there for oxygen. We talked about Hund's rule, which again states that the kind of most stable form of how the electrons go in there is to maximize that sort of parallel spin or unpaired spin. And again, that's why what we were talking about when we have multiple orbitals in a subshell, we go one at a time in the upwards direction, parallel spins, and then come back and pair off at the end. And again, that's important in terms of the order at which those guys go in there. We obviously drew some orbital diagrams as well. And you can see sometimes people will use boxes to represent those. And again, that's basically Hund's rule there, one at a time as we were doing, and obviously coming back and filling that up. Okay, so let's talk a little bit about some important electrons that we do see when we talk about electron configuration. And for example, if we look at oxygen here, for example, which is number 8, valence electrons are the outermost electrons. They're the ones in the highest energy levels, kind of furthest away from the nucleus. They're important because, as we'll talk about in the bonding chapter, they are essentially the ones that are involved in bonding. So they're the ones that are involved in bonding. So if we look at this sort of configuration here, we can see that when we look at this, we have basically 2 electrons here on the first energy level. And then on the second energy level, we have 2 electrons. And also on the second energy level, we have 6 electrons. So these 6 electrons are the valence electrons. These 8 electrons are the valence electrons on the second energy level. These lower energy ones are sometimes referred to as core electrons. Core electrons are ones lower in energy, not involved in bonding, and our valence electrons are the ones in the highest energy level. We just did, I think, looked at sodium, 1s2, 2s2, 2p6, 3s1. We have 2 electrons on the first energy level. We have 8 electrons on the second energy level. But here with sodium on the third energy level, we have 1 valence electron, basically. And that would be 1 valence electron here. Now, you can definitely write out the electron configuration like that. These would be the core electrons below the valence electrons. Our much easier way is if we look at the periodic table, this is, group 1, group 2. Sort of skip the middle there. 3, 4, 5, 6, 7, and 8. And just to give some reference to where we're at, again, this is like lithium, this is beryllium, over here is boron, carbon, and obviously nitrogen, oxygen, fluorine, and neon. So when we talk about groups on the periodic table, that's going up and down. And group 1 actually does start with lithium, although in a lot of periodic tables, hydrogen will be hanging out there. But lithium is actually part of group 1. Group 2 is right next door where beryllium is. This is the transition metals, as we'll talk about. We skip that whole middle section where there's like SC, TI, CR, FE, all that kind of stuff. Picking back up where boron is group 3, carbon group 4, nitrogen group 5, oxygen group 6, fluorine group 7, and neon there. Looks like nitrogen again, but neon at the end there is group 8. And the number of valence electrons actually equals the group number. So everybody in group 1 on the periodic table will have 1 valence electron. Everybody in group 2 will have 2 valence electrons, and obviously 3, 4, 5, 6, 7, and 8 valence electrons. The exception being actually just helium here, which is above. Helium only has 2 electrons total, so it doesn't have 8 valence electrons, but everybody else will have 8 on that group. So if we look at sodium, sodium is group number 1, is right underneath lithium. It has 1 valence electron, which would be this one. If we look at oxygen, which is group number 6 on the valence electrons, it would have 6 valence electrons. I'm sorry, 8 valence electrons. I'm sorry, in this case, wait a sec here. I'm sorry, this is this is not oxygen. This is obviously neon there, which is 10. I should look at that, right? So that is neon, which is 10, which has 8 valence electrons, which is what we see. Oxygen, which is this, 1s2, 2s2, 2p4, this is oxygen, has 6 valence electrons, which are these guys right here. 2 and 4 is 6. Thinking that was oxygen there, but that is neon there with 10 electrons and has 8 for its valence electrons in that case. So that's a much easier way to sort of figure out how many valence electrons. It does equal basically the group number. Any questions on that there? So valence electrons, outermost electrons equals the group number. The highest sort of energy level electrons as you have in your electron configuration. And core electrons are the ones in lower energy level than the valence electrons. And the valence electrons are really important because they are involved in bonding. When we look at the periodic table here, there are some different groups or blocks. And you could actually, if you wanted to, sort of use the periodic table to count out your electron configuration. Now, when we think about the s block, right, and s orbitals could basically hold 2 electrons, and that is group 1 and 2 on the periodic table, 1 and 2 electrons. That's basically what those 2 guys represent. The p subshell can hold a total of 6 electrons, and that is over here. This is 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, and 6 electrons. D's can hold 10, and that's over here in the transition metal region. 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7 electrons, 8 electrons, 9 electrons, and 10 electrons. And F can hold 14 electrons, which are actually the 2 rows that are on the bottom there. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons. If you remember, we talked about the energy levels, or the N number goes through 1 through 7. If you look at the periodic table here, that is 7 rows or periods. So the 7 periods that you find on the periodic table, periods go left to right. So going left to right are periods. They represent the N number when you do electron configuration, or the principal quantum number. And you literally can use the periodic table if you know what you're doing. I say if you know what you're doing, to actually count off your electron configuration if you want. So to kind of show you how that would work, perhaps we will look at sodium, which we just did. 1s2, 2s2, 2p6, 3s1. So if I were to use the periodic table to sort of count off sodium here, just kind of clean that up a little bit on my marks. We would actually start at the top of the periodic table. do green, I think. All right, so starting up here, this is period 1. So this is 1s1 all the way over 1s2 to there. Coming here, this is the second one. So this is 2s2 to there. So that takes care of that and that. Coming over here, this would then be 2p6, which would be there. And this box right here is sodium on the periodic table. That would be 3s1. So you literally can count off sort of electron configuration. Again, if you kind of know what you're doing, you would be okay. And what I mean by that is, let's take a look at, for example, something like iron. Iron is number 26 on the periodic table, and that is 26 protons, which also means it has 26 electrons. And if we write the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And by the way, iron is right about there is iron. So let us see why I say you need to be careful here. Let's take a look at this and let's try to count off iron to get ourselves there. And if we do that, starting up here, 1s2 is good. 2s2, overjumped it, that's good. 2p6, 3s2, 3p6, 4s2. And now if you don't know what you're doing, you go, oh, I'm on 4. This is 4d6, which is not what it is. And that is because the d orbitals actually start on the third energy level, which means when you're looking at this box here, this guy right here, this is actually 3D. This would be 4D, this would be 5D, and this would be 6D. So if you remember when we did the zigzag guy that we made, we actually only did D up to 6. And that's because that is what it basically encompasses. So that's actually 3D6. And you got to be careful not to call it 4D6. The D's are 1 behind the period number. So the D's are 1 behind the period number. Now, you could also see that these guys over here, by the way, these two rows actually go right here where the arrows are, which means these are the F block. This is actually the 4F and 5F block, a row. And that basically means that the Fs are actually 2 behind the period number. So there is a little bit of, you really need to understand what's happening if you want to try to count off electron configuration using the periodic table. I personally recommend not doing that and maybe just using it to check yourself. You most likely will never go wrong if you just recreate this thing like we saw earlier and we used earlier, because that will definitely put you probably in the correct sort of order that you need without sort of messing yourself up by looking at the periodic table. You could use it again to sort of check yourself, but you will always sort of be okay if you kind of use this guy. You could be okay here as well, but you do have to kind of keep those couple of things sort of in mind, and it gets a little confusing sometimes and you could make some errors. So I would recommend probably using this more as a double checking sort of method than maybe your sole method of how you're doing electron configuration. Question on that there. Okay. All right, so let's see here. what I think we will do is we will stop here. I think for now, that's enough torture, I think, for today. And we'll talk about a couple of things here. Give me 1 second here just to make sure. Yeah. I think I'll be okay. Okay, so I think what we're going to do is, as I mentioned before, just so everybody's on the same page, what we're going to do is okay, so we are going to have, I think, a quiz. So we should do that before I forget to do a quiz, I suppose. Would be good. So let me actually go, I guess I'm just, that's not bad. So we're going to quiz on Monday. Quiz 1 will be on Monday. It will cover chapter 1 and 2 up to what we just talked about today. So what we just finished up. So up to today's lecture. So that will include basic electron configuration, orbital diagram, quantum numbers. So that will cover up through sort of what we talked about up today. We still have a little bit more to talk about electron configuration with transition metals and stuff like that, but we'll talk about it next time. And the periodic table and some periodic trends, I think is what's left in this chapter. So we'll cover that on Monday. So we will take it on Monday. We will do it actually at the start of lab. So the way this is going to go is we will have lecture like normal on Monday. So we'll do our normal lecture. We'll take a break and we'll do the quiz at the start-ish of lab there. The quiz will require, again, for you to obviously have your camera on, your work area and everything like that clearly being shown. And we will take the quiz together. Afterwards, we'll take a little break, or after we're done with the quiz, we will then talk about experiment 3. And we'll do experiment 3 because hopefully by the end of lecture on Monday, we should cover everything that we need for experiment 3. So tentatively, we will do experiment 3 after the quiz. Stuff like that. And that should be okay because then Tuesday is about significant figures, and we'll just do the significant figure sort of talk with the study assignment that kind of goes with it. Any questions on that? A reminder that, again, you will not be provided any formulas from these chapters, but you will be provided any type of constants. So again, like Planck's constant, speed of light, any type of conversions like nanometers, those type of things will be provided for you. Things like C is equal to the wavelength times the frequency will not be provided for you, and those type of formulas. Any questions on that? I obviously haven't written the quiz, but probably a few questions, 3-4 questions, probably mainly I would think workout type problems. And that's probably what the quiz will be sort of composed of. The quiz will be a written quiz, so it will be like a PDF file that you'll open up in the meeting with me and you'll work it out. Yeah. And obviously you'll need to show your work and stuff like that. So you can either go print the quiz and obviously work it out, or you can work it out, I guess, on a piece of paper. Other questions on that? Okay. So I think that about covers, like I said, we're almost actually done with chapter 2. We've got a few more stuff to talk about, a little bit more about electron configuration and stuff on Monday, and about the periodic table and some periodic trends. We'll finish up chapter 2 on Monday, and that will actually kind of wrap up almost pretty much the material for exam 1, which, if I'm not mistaken, is a week from Monday. So just keep that in mind. So this quiz is probably a good idea to keep you on pace, I hope. So we'll take the quiz again Monday during lab time at the beginning. We will have lecture like normal on Monday. And then after we're done with the quiz, we'll kind of all meet back up, obviously, in the lab. And then we will talk about experiment 3, and we'll knock out experiment 3 on Monday. Any questions on anything?